All right, so we're now going to topic 2.3, which is on the topic of magnetic fields. So again, we're talking about a field which has got to do with a potential to do work, but this time around of a magnetic nature. You find magnetic fields share many things, the same with electrical fields, with some fairly distinct characteristics. Okay. Later on, I'll be turning on the webcam, which shows some hand gestures as well, because you're going to be using your right hand in many of the things we do. All right. So topic 2.3 is on the page 162. So page 162. And we're going to be talking about a few concepts that you might be familiar with or might not be familiar with. Okay. So magnet. Okay, first of all, we talked about charges in as in electrical charge. Okay, so you got positive charge, sometimes you have negative charge, and then you're going to have field lines that go like this. So if you have small positive charge, this is field lines that it's going to experience. So as a recap, field lines means at any point in time, a small positive unit charge is going to experience a tangential direction of the force. Okay, so if there's a little charge in between that doesn't affect your surrounds, it's going to have a force pushing in that direction. All right, so now magnet. So one thing about electrical field is the fact that you can have a positive charge or negative charge existing in isolation, or you can have a lot of positive charge, a lot of negative charge existing in isolation. With the magnetic field, or in the case of a magnet, okay, so in the case of a magnet, you're always going to have a north direction and you're going to have a south direction. And quite often, what you see is a magnet drawn like this, where the northern side is the north side is generally in red, and the south side generally in blue. Okay, so now since they always exist not in isolation but together, you're going to expect some form of magnetic field lines, which if you ever seen little fluff of magnetic material around the magnet, that's what that will look like. So similar to similar to electrical fields, the kind of field line you'd be expecting is always going from north to south. Okay, so and a similar idea is if you got a charged particle in here, so if you got a positive charge, that's the direction you're trying to go. Okay, it's tangential with or the tangent direction to where the field line is going. So you can't go inside the magnet, but we'll look at ways we can make an electromagnet, and inside will be a little bit different. Okay, so that's what a magnet does. Now, what happens if you have multiple magnets? So say if you got a north, so you got one here, and that should make this one north, and let's make this one south, make this one south, make this one north. Okay, so north is always good. The field line is always going to go from north to south, and there's nothing stopping it from um, going from one magnet to another. Okay, and which is now when you have this situation here, it's almost like parallel plates in electrical field. So again, it's that parallel. Okay, so now south and north can't coexist by itself. It must it must appear in pairs. So south is we're going to have things go like this. Okay, it's always coming out from the north, coming out from the south. And again, one thing to keep in mind of is the what you call the line density. Okay, in a linear or on paper, the more dense the field lines is, the higher the magnetic field strength, which is something else we're going to discuss in a moment. Okay, so now magnetic field. Okay, so a magnet exhibit some form of magnetic field. In fact, what we know, and this is a very important definition, is any moving, okay, the keyword is moving charge exert magnetic field around it. So now key thing is a moving charge. Okay, so if a charge is not moving, then it doesn't have doesn't have a magnetic field, doesn't generate a magnetic field. So I'll go to our favorite parallel plate, which you learned from the previous topic. Now all the charges here and all the charges here are static, means they're not moving. So you're not going to generate a magnetic field. However, since static electricity or electric charge still exert a magnetic field, you're going to have electric field line like this. Okay. All right, I've already explained field lines, so I'm going to delete this. Okay. So, however, if you got a say an electron that's moving in this direction with the velocity v, then it's going to generate a magnetic field. Okay, so and the relationship of a magnetic field goes like this. A magnetic field is denoted by the symbol B, B for basketball. Okay, and again, it's also a vector field. So magnetic field is expressed by mu naught divided by 2 pi, and this is a constant. Okay, so you don't need to memorize it. So and multiply by I divided by R. This is a special case for a thin wire. Okay, so if you got electricity going through a thin wire, then this is a magnetic field, which means it's the force per charge. Force per charge going through. Sorry again. Force per charge around the wire. Okay, and I'll go through a bit more of that in a second. So, I is the current, the conventional current, which means it's positive. Oh, we don't want that. No, we don't want this. Current, which is measured in amperes, and it's conventional current, so it's always positive. It's positive, so it's an opposite direction to how the electron are traveling. Okay, and you got your R, which is the radius from the wire, which is measured in meters. Okay, and not to forget, this is a constant. Mu naught, I believe, the permeability of free space, and 2 pi was 2 pi. So this unit here is 2 times 10 to the power minus 7. Okay, and the magnetic field is measured in unit of T. Okay, it's measured in T, and we've got one fairly awesome fellow. His name is Tesla. So T is Tesla. It's a unit for magnetic field strength. Okay, so the significance of this is, say, if we've got a straight wire, okay, and that carry the current I, it's going to have a magnetic magnetic field around it. Now, exactly what does the field line look like is what I'm going to demonstrate on camera. Okay, so actually, I'm going to, first of all, if I got my eye here, okay, I'm moving, the current is moving towards me, then the electric current is going to be, this is anti-clockwise. Okay, how do I know it? How do I know it's anti-clockwise? You gotta use something called what we call the right-hand rule. Now, before I go on camera, I just want to bring it over to your workbook, and that tells you a little bit more information. Okay, so all right, so The right-hand rule goes like this. So if I got my current going up, okay, then I pull my right hand around it. If I put my right hand around the wire, then my fingers are going to they're going to tell me what direction the electric field is going. Okay, so in this case here, you got to do your little you down your little thumbs up here. Okay, your thumbs up is saying that, well, since your fingers are going around in that direction, okay, so the field lines are going to go in anti-clockwise, okay, anti-clockwise around the about the wire. Okay, so let's go over to the camera and use that to illustrate better. Okay, so all right, so this is my right hand, and say this is the direction the current is traveling. All right, so if I have something to hold on to, so this ruler here going towards your right is where the current is going. Again, that's conventional current, which means your electrons actually going that way. Okay, so if I now put my hand or my fist around it and have a thumbs up direction, okay, my thumb is now going over the current direction, conventional current, okay, and the fingers are wrapping around the wire, which means if I now look at this way, you can see that it's actually going anti-clockwise. Okay, all right, so 1 second. I'll take a photo of this. All right, and all right, so now since the way I'm holding it, remember my thumb is actually going towards, my thumb is actually going towards where the current is going, which is out of the screen. Okay, just and now if I change color pen, the direction of the magnetic field is going to be anti-clockwise. Okay, it's going to be anti-clockwise all the way around like this. Okay, so which means if I got a little charge, okay, sitting right here, right, if I got a charge sitting right there, remember the charge is a positive charge, small positive test charge. The magnitude of, the direction of the magnetic field strength is going to push it in that direction there. Okay, now if my little test charge is now over here, okay, then the direction of the field is going to push it that way. Talking about wrong pen at the wrong time. All right, so, and one thing that we know that's probably not easily expressed is the fact, and just let me go back to the whiteboard again, is the fact that, we'll go through that in a second, the further away you are from the wire itself, right? I'm going to use this to illustrate. Okay, so that's just saying that you have current going out of the page, which is similar to the example we had before. Okay, you have your field lines going in the anti-clockwise direction. Okay, the further out you are, the less field strength you're going to experience. So if I'm over here, I might only experience a little field strength. If I'm over here, I'm going to experience a little bit more. Okay, the further away you are from the middle, okay, because this distance here is r, okay, and recall our equation of B equals to permeability free space divided by 2 pi times it by I divided by R. Okay, the greater the R, this one is gonna, the field strength B is gonna be less. Okay, and that's assuming the current stay constant. And as we expect, if you have a higher current, then you're going to have a stronger field strength, and that's proportional to the permeability, the constant that we have here. Okay, one thing not to be forgotten is the notation if you're working in 2D, trying to express 3D. Okay, if you got like solid dot, yeah, that means the current is coming out of the page. Now, if you got like a cross in between a circle, that means the current's going into page. So in this case here, you imagine that the current is actually going into the screen. Okay, now how do you remember this? The way I remember is this one here looks like a target. So since it looks like a target, it's going into the page, okay? And so the other one must be coming out of the page. Okay, so but most of the time, if you only have one single, if you just have one single wire, it's not going to, there isn't really a lot of magnetic field strength, and you can't really use much of the circular field like this. So people manipulate the wires in different ways to try to get it to show different things. Okay, so let me go to this page here. Okay, so if you start hooking the wires around, okay, and just let me illustrate using something I pre-prepared. Okay, so in figure 2.3.16, it's showing that if you make the wire into a loop, okay, so similar to, okay, if you make it into a loop like this, all right, if you make it into a loop like this, okay, and if I draw it, it's going to look like this, okay, and I just say current is going in that direction. All right, so what's going to happen is all around the loop, you're going to have, say, remember if I apply my right hand rule now, okay, around here, you're going to have, if you cover around, the fingers are pointing down, okay, the fingers are pointing down into the page, okay, and as I come around the loop over here, okay, my thumb is still pointing towards where the current is going, and my fingers are still pointing inward. And if I'm on the left hand side here, yeah, that's similar. Oops, it's more like this. So which means if I now look in 2D, okay, the magnetic field is constantly going into the page within the loop. Okay, so inside the loop here, it's going to the page. So I should have lots of these to show you that the field lines is going into the page. Okay, but on the other hand, if you, okay, I've still got my right hand here, but on the outside, right, see how on the outside, then my fingers are actually pointing up, okay, out of the page, out of the page, out of the page, which means on the outside, you're going to have the electric field going out of the page. So inside this loop here, I'm gonna have a lot more concentrated electric field going into the page. Okay, and that's something we can use. Okay, so going back to the workbook here. All right, so if you have a loop like this, okay, if you got a loop like as this is looking in 3D, so the current going in, hang on, going from here, come all the way around, come out this way, okay, then apply my right hand rule. The field lines are going to come out like this through the inside of the loop, okay, and which means if I now have a test charge around here, it's going to experience a lot more force than just a single wire. Okay, so and what I've just drawn is simple, it's illustrated in figure 2.3.13 here. Okay, so using a single loop, I can concentrate a lot more field strength in the middle, sorry, inside the loop. Okay, now you will probably have seen something called a solenoid. Okay, solenoid, it's really a lot of different loops. Now you're not going to get perfection because it's not going to be completely parallel. Each of the loops are not going to be completely parallel to each other. However, this is going to be close enough. So not only you're concentrating, so looking into solenoid. Okay, so I'm looking. This is the front. I'm now looking into it. Okay, you're going. Not only you're going to get a lot more concentrated field strength in the middle. You also do that several times. Okay, because you depends on how many loops you have. All right. So in the case of a solenoid, it's like several concentric and close to parallel loops around. You're gonna get a lot of field strength in the middle. And in fact, if you do that, okay, many cores of wire, you basically made what you call electromagnet. Okay, so so if I have current going in there, okay, and let me make a quick loop and you can see. Okay, this is not perfect, but all right, so right now I've got a bit of a solenoid. Okay, so that looks like this. All right, and if current is going in from here, right, so current going here, oh, come on, coming around, coming around, coming around. Okay, if I pull my right hand rule on it, if I pull my hands around, okay, so on the inside, my field strength is going that way. Okay, that makes this side, okay, the left hand side the north and right hand side the south. North because if you have a little test charge over here, it's gonna want to go that way. Okay, and just like if you have a magnet, and this is north side, this is south side. Okay, so this is how to make electromagnet. So you see a solenoid is basically making a little magnet. Okay, all right, I've got a little simulation which I'm going to show you. Okay, which demonstrate the direction that of the field. You open an electromagnet. All right, so this is standard magnet. Now electromagnet. Okay, so in this case here, you can see that if this is flow electron, I'm going to turn it off. Okay, so this means that if basically if a magnet is being put over here, all right, that means this solenoid is going to make north the left. All right, let me mark up on it. All right, so this magnet is going to make that side there the north. That's, oh, change color. That side there the south. Now the reason for that being, if you put your right hand around it, okay, if you put your right hand around it, then if your thumb is pointing down, oops, your thumb is pointing down this way, your little fingers are going to come through this way. Okay, and that's the direction of the north. Now, and hence, if you put a compass there, then your north is pointing in that direction. As I come around, okay, since the field line is not going that way, the north is going to point that way. Okay, all right. So this is a basic example of how a magnetic field will work. Next topic, we're going to look at charge particles in a magnetic field. Now, importantly, there's a few questions, but there's only one equation, which is generally calculating B. Okay, and next topic, we're also going to see what B looks like for a solenoid, and we're also going to look at what the force is going to be like depending on the magnetic field strength. Okay.